Hey guys, so today we're going to learn about inertia, Newton's first and second laws. One of the first things that we need to talk about is the idea of balanced versus unbalanced forces. And in balanced forces are when all of the forces acting upon an object are equal, and as a result of that, the object will not accelerate. So, for example, the boat here is the system, and the truck is trying to pull the boat, but is not able to. So, what we know for sure is that the boat itself has a couple of forces that are already acting upon it before the truck tries to pull. One of those would be gravitational force. So it'd be Fg on the boat by the earth. And another one of those would be the normal force on the boat by the ground. And because the boat is not falling into the earth or going above the earth, they have the same amount of the tick marks so that the force is the same. And then we also have, at this particular case, the truck is trying to pull the boat. So that would be the force of tension, or tension force on the boat by the truck. And acting against it would be the force of friction. And so that would be the force of friction on the boat by the ground. Okay. And because the boat is not moving, the number of tick marks would be the same. So that's when you have balanced forces. So when the object is not moving in any direction or accelerating in any direction, all of the forces are the same or canceling each other out. Then you have unbalanced forces. And so in this case, the boat is the system, and the truck is pulling the boat to the right, but it happens to be going slowly. So two of the forces are going to be the same. The normal force will still be the same. And the gravitational force will be the same. And the number of tick marks will still be the same. But this time we have the force of tension, which I'm going to draw the same as I drew before. So it's going to be force of tension on the boat by the ground, or I'm sorry, by the truck. That's gross. Let me try to write that so it doesn't look awful. And then we have the force of friction. The force of friction here on the boat by the ground. Force of friction on the boat by the ground. So when I put tick marks on this, I'm going to have the more tick marks from the truck on the boat than I'm going to have on the friction on the ground. So that indicates to me that the boat is moving or accelerating, and it's accelerating with the truck at the same time. So that brings us up to the idea of inertia. And inertia is an object's resistance to its change in motion. And so the more inertia an object has, the harder it is to move or to stop. So what that means is that that definition brings us to Newton's first law of motion. Newton's first law of motion says that objects at rest and objects in motion will stay at rest, or they will stay in motion and in the same direction and the same speed unless acted upon by an unbalanced force. So, and I'll link a I'll put this in the note page with the GIF that actually works. But what happens here is the car's not tied down. The truck starts to move. The car doesn't go anywhere and actually falls off. So the truck is moving, but because there's no force being acted upon by the car stays in one spot. The example in the middle is a person actually falling on a trampoline. The trampoline is covered with leaves. The person on the trampoline go down, and the leaves appear to stay in the same spot because they are obeying Newton's first law of motion. And then we have Mr. Test Tube Guy over here on a skateboard, and Mr. Test Tube Guy over here when his skateboard hits a rock, the skateboard stops, but Mr. Test Tube Guy keeps going forward and falls and breaks, which is sort of funny, I guess. So that's Newton's first law. Other examples of Newton's first law, again, objects at rest will stay at rest, objects in motion will stay in motion, are things like the old-fashioned pull the tablecloth out from underneath the dishes, or in this case, the book and the vase on the table. The young lady pulls the tablecloth really, really fast, and because there's very, very little friction on the objects on top, the book and the vase stay in one spot, and the tablecloth is moved. So the book and the vase are obeying Newton's first law of motion of being at rest. In the car crash example, the crash test dummy, as the car collides with the wall, the crash test dummy continues to move forward and hits the steering wheel, or the airbag rather, and so as a result of that, during Newton's first law of motion, the car stops. So it's also obeying Newton's first law of motion, but the crash test dummy keeps moving, also obeying the first law of motion. Now, Newton's second law says force is equal to an object's mass times its acceleration, or the formula that you're going to be working with is F is equal to m times a, which says that if two objects of different masses are hit with the same force, the less massive one will accelerate faster. So what that means is if I take a ping pong ball and a bowling ball, and I hit the ping pong ball and the bowling ball with the same force, the ping pong ball will go faster. And the other point here is that a larger object requires more force to accelerate the same amount as a smaller object. So if I wanted them to go the same speed, the ping pong ball and the bowling ball, I would push the ping pong ball with very little force, but the bowling ball with a lot of force to make them move at the same speed. So here are some examples. The hammers in this case are the same, indicating that they are giving the same force. Bowling ball, let's say that's 10 pounds. Basketball, let's say it's half of a pound. If we hit them at the same rate with the exact same force, this bowling ball is going to accelerate faster than the basketball will accelerate faster than the bowling ball. And here I have the hammers, and the hammers are two different sizes, indicating the bigger one indicates a larger force, and the smaller one indicates a smaller force. So what that means is that if we hit the basketball and the bowling ball with different amounts of force to compensate for their mass differences, the bowling ball and the basketball will accelerate at the same rate. So here we have an instance where more force is being applied to the bigger object or the heavier object, and less force is being applied to the lighter object, so they both move forward at the same rate. So here's some practice that you're going to have to be able to do. You have to create a force diagram for the car being pushed to the right at a constant speed, not accelerating. You're supposed to choose appropriate labels, directions, and lengths for the vectors. So in this case, the system in question is the car. And the fact that there is force being added to it is important. But in this particular case, it's not accelerating. So the first thing that we always can draw is we can draw that there is some gravitational force. So that's the force of gravity acting upon the car by the Earth. And we have the normal force. Force normal acting upon the car by the ground. And then we have the there's also the normal force. In this case, the normal force of the human pushing. So the force of normal on the car by the human. And then we also have the force of friction, which is acting on the car, force of friction, acting on the car by the ground. And in this case, because the car doesn't rise or fall, it would have the force of gravity and the normal force have the same number of tick marks. And because the car is not accelerating, the normal force of the human pushing on the car and the force of friction on the human on the car by the ground would also have the same number of tick marks. Here we have one more example where we're creating a force diagram for the cart. Well, the cart being pushed to the right and speeding up, so it is accelerating. And so we're going to choose the appropriate labels. And just like we've done in the past, we are going to apply gravity. This time I'm going to make it a little bit shorter than the car because hopefully this shopping cart will be less massive than the car. So the force of gravity on the cart by the earth, and the normal force on the cart by the ground. And because it's not floating up or sinking down, those are going to be the same. And then we have the normal force over here, force normal on the cart by the human, and the force of friction on the cart by the ground. And so this time, because the cart is accelerating, I'm going to give it, say, 3 tick marks, and the force of friction 1 tick mark. So that indicates that in this particular scenario, the cart is moving, it appears to be from left to right at an accelerating rate instead of not accelerating or staying still. All right, so your homework is to work on the worksheet that is attached in the email. It's also on Google Classroom. And that worksheet is about either calculating a force or calculating a using the Newton's second law, the force is equal to mass times acceleration, or drawing some diagrams that indicate whether or not an object is accelerating. And you should be able to turn that in on Google Classroom, and hopefully that won't be too difficult. Have a nice day and enjoy the rest of your week.